Aren't you glad you don't have a big claw like this guy? You can thank symmetry for this. Or have one side big like this guy and the other small. This is all symmetry. Today, that's what our lesson will be on. In this video, I will explain the meaning and significance of the number of terms in a polynomial, the degree of a polynomial, the meaning of an even and odd polynomial, and an even and odd function with respect of symmetry, and finally, the end behavior of a polynomial. Polynomials are the sum of variables and exponents. Each added piece is called a term. Under the rules of a polynomial, the exponents must be raised to whole numbers. This is not a polynomial because the variable is in the denominator. This is not a polynomial because the variable is raised to a negative exponent. This is not a polynomial because the variable is inside a radical. So what is a polynomial? This is a polynomial. As explained earlier, each piece of a polynomial is called a term. This example has 3 terms. The difference between an even and odd function can be determined by the degree of the exponents of all the variables. This is an example of an even function because all of the variables are raised to the power of an even number, 4, 2, and the constant is raised to x to the power of 0. We can test whether it is being even by determining if f of x is equal to f of negative x. When the variables are being subbed in as negatives, it will become positive because of negative times a negative becomes positive. Thus, we get the same function as a positive x subbed in. This is an example of an odd function because all of the variables are raised to the power of odd numbers, 5, 3, and 1. We can determine if the function is odd if of negative x is equal to negative f of x. Where the variables are being subbed in as negatives, the term will become negative. Thus, when a negative variable is subbed in, it is equal to a negative of the original function. An even function is symmetrical with respect to the y-axis. A positive even function will have the end behavior increasing on the y-axis infinitely going up through quadrants 1 and 2. A negative even function will have the end behavior decreasing on the y-axis infinitely going through quadrants 3 and 4. If we split the even negative function down the y-axis, it would be symmetrical. Testing odd functions. A positive odd function will pass through quadrants 1 and 3. If the function is twisted 180 degrees on its origin, it will remain symmetrical. The function will continue on infinitely on the y-axis in quadrants 1 and 3. A negative odd function will pass through quadrants 2 and 4. If the function is twisted 180 degrees on its origin, it will remain symmetrical. The function will continue on infinitely on the y-axis in quadrants 2 and 4. An odd function is symmetrical with regards to the origin. That's it for today, so remember, even functions are symmetrical on the y-axis, which can be represented by f of x equals f of negative x. Odd functions are symmetrical on their origin, which is point symmetry. We can check by f of negative x equals negative f of x. Thank you.